Okay, now let's get to some of our more familiar alternative energy sources. The first one is solar power. When we talk about solar power, we're not just talking about solar panels, although solar panels are certainly one of the most common ways. Solar panels are really what we call photovoltaic cells. They're semiconductors, and what they do is they absorb the photons from the sun, they absorb that electromagnetic energy, and they convert it into electrical energy. It uses the science related to the photoelectric effect, and it's in some ways similar to how a charge-coupled device, a CCD, that would be in your digital camera, how that would work. There are multiple layers. The sunlight hits, it absorbs those photons, and electrons start to move. We can also use solar heating panels. And the way this would work is you have water that's in a number of tubes, and generally they put these on tops of houses so they can get a lot of sun. The sun heats the water that's in those tubes, and then it passes through a pump system to heat water that's inside your house. In this type of system, the water can get up to as high as 158 degrees Celsius. Obviously, with solar power, it's not consistent because we have to have the sun shining in different places on the surface of the earth and in our country and all around the world. The regional variations can be significant. You don't always get the same amount of sunlight. You don't always get the same intensity. We can be at different distances from the sun at different times of the year. As the length of the days and nights change, it becomes difficult to get a consistent amount of solar energy. So you have to be able to store it in some way. And storing solar energy can be an expensive proposition. We're going to talk about this a little bit more later on, but you also have what we call the solar constant, and this is essentially the amount of incoming energy from the sun. And again, it depends on where you are on the surface of the earth as far as how much energy you actually get. Closer to the equator, you get more intensity, you get more energy per unit area because the sun's rays are much more direct. When you get further north or further south away from the equator, as the angle of the earth changes, you get less direct sunlight, so that solar constant decreases. Then we have our hydroelectric, and hydroelectric is simply using water, hydro, to produce electrical energy, hydroelectric. And there are a number of ways that we can harness water to generate energy. The most common is through dams. And in order to use water in this form, we dam up a lake or a river, and it raises the level of the water. It increases the water level, so you have these deep areas. You have water that's up at a higher elevation. And then the water is allowed to flow through what we call penstocks, which are just essentially long tubes that have gates on them that can control the amount of water. As that water flows through the penstocks, it turns turbines. The turbines generate electricity. The basic process here is the hydroelectric dam is taking the potential energy that's in the water being held behind the dam, allows it to flow downhill through a turbine, and it converts that potential energy into kinetic energy. The kinetic energy turns into mechanical energy as it's turning the turbine, which then turns into electrical energy. Okay, so here's a diagram of how an hydroelectric dam works. We have our reservoir up here in the upper left, and so our water level gets raised. We have our penstock, which is basically our long tube, and there's a filter or a gate here that allows water through. Water flows down through. It's losing potential energy. It's gaining kinetic energy. As it passes through the turbine, it causes the turbine to spin. As that turbine is spinning, it's spinning its generator. It's creating electrical energy. It passes down through the river. And then, of course, our electricity gets sent off to the grid. The hydroelectric dam is a clean source of energy in terms of not generating carbon dioxide, not affecting our non-renewable resources, but it certainly does have environmental impact. When you dam up a river, you're completely changing that ecosystem. You're stopping fish and other organisms from moving freely up and down the river that they may normally once have done. You're flooding an entire area because it's generally damming up a river, which then turns that river into a very, very large lake, and that lake is going to flood all of that low-lying area. So you're chasing any animals out of that area that's being flooded, so you're completely changing the ecosystem of the area. Even though you're not generating carbon dioxide, things like that, you're still having an impact. Another way that water can be used to generate electricity is through the tides, through tidal water storage. And this is big in France and Russia right now. They're building a number of these. And the way this works is that dams are built along the coast. And as the tide is coming in, sluice gates are open, and the tide rolls in and it fills up this storage area. Once it's reached high tide, the sluice gates get closed, and it traps all that water behind the dam. Once the tide has gone out, now this water that's been confined gets released through the penstocks, and just like with a regular dam, the water passes through the turbines, generating electricity. And so this is kind of a novel idea because it doesn't, other than the actual construction of the buildings, it's not directly affecting the surrounding environment. You're not flooding an entire area. You're simply trapping water that's come up and then letting it back out through. And it's been working fairly well for them. Again, the problem, though, is that you're reliant on the tides. Now, in these hydroelectric scenarios, when there's off-peak hours, when not as much electricity is needed, they can use the excess electricity that's being generated to actually pump water from lower reservoirs back up to the higher reservoirs, where it can then be used for peak times or when they need more electricity. So we can roughly calculate the power generated if we know the flow rate of water and some of the properties of water. We know that power is energy per unit time, and when we're talking about hydroelectricity, remember we're talking about water and we're talking about potential energy, and our potential energy is mass times the acceleration due to gravity times the change in height. Well, our mass of the water we can put in terms of density and flow rate. Mass per unit volume is density. Volume per unit time is what we call flow rate. And so if we factor those two in, we end up with mass per unit time because our volumes cancel out. Or we can rearrange it here, and you can see at the bottom the little lowercase rho, which is the small looking p, times g times change in height times volume per second. The lowercase p is density. That's just another symbol for density. Volume per second is our volume per unit time, but again, depending on the material we're given, we don't need the specific volume if we have the mass and the time. Then we have wind power, and similar to solar power, it's clean in that it doesn't produce carbon dioxide, but again, you're reliant on wind, which isn't always consistent, and so it's important to pick carefully when you're deciding where to put wind farms. It has to have a certain amount of wind in order to make it worthwhile. Again, though, it's really kind of an indirect solar energy system because the wind is produced by the uneven heating of the surface of the Earth. So the sun's heating the Earth unevenly, and that's what actually causes the winds. The difference is in air pressure. And so we make use of that. We stick up horizontal axis wind turbines, and you can see the picture in the background. And they generally have very, very long, large blades. And as the wind blows through them, those blades turn. Those blades are connected to a turbine, and as the turbine turns, it generates electricity. So again, we're converting mechanical energy into electrical energy. And most of these, the direction that they're facing can be changed. So they can rotate if the direction of the wind changes, so they can always make the most use of the wind. And this is just a diagram, a real basic diagram of the internal workings. You've got your rotor blades, which are the fan blades here. Usually they're a 3-blade system, 3 or 4 blade system. And then within the shaft you have the generator, which gets turned. And in the transmission you generally have a series of gears that allows the speed of the internal workings of the generator to be controlled, since the rotor blades are not always going to be spinning at the same speed, but you want a consistent speed in your generator, and so the transmission allows for the control of that. And experimentally it's been found that the power output of these wind generators is directly proportional to the area that the blade sweeps out. So if you think about those blades sweeping out a big circle, that's our blade area. And it's also directly proportional to the cube of the wind speed, so the speed of the wind to the third power. And if we work that out, the area swept out by the blades is pi r squared. Again, that's the area of the circle using the length of one of the blades as our radius. In 1 second, the volume of air passing the blades is VA, the velocity times that area. The mass of the air passing the turbine in 1 second then is P, where P is the density, and actually that's a rho, a lowercase Greek letter rho, times the velocity times the area. So the kinetic energy that's available each second, again we know is 1/2 mv squared. If we solve for the mass of the air is the area times the density times the velocity. And again, here's where we get that velocity cubed. So the energy in the turbine is 1/2 A times rho times V cubed. And that's our power available. And then finally we have wave power. And wave power is a little different from hydroelectric because we're not storing up water, we're actually using the wave motion, the up and down motion of the waves, to generate electricity. And there are a number of ways, but they all have to do with having floating objects sitting in the waves that are tethered to the ground that can oscillate back and forth. The two on the bottom here, what we call, the one on the bottom left is a Boyd-Moore device. And it's attached here, and this little bobber goes back and forth, oscillates back and forth as the waves pass through it. As it oscillates back and forth using a series of gears, it causes a turbine to turn, again generating electricity. Same kind of idea over here. We have hinged contour devices, which are longer and flatter, but they again kind of oscillate back and forth in the motion of the waves, and that motion is converted into electrical energy. And then we have what we call oscillating water columns. And these are long columns that are generally moored to the floor of the ocean. They can also be built into cliffs on the shore. And as the water enters a chamber, the air is compressed. And let's actually look at the diagram of these. As the wave comes in, this water level rises and it compresses the air. And it actually drives the air. And you can see how our openings here are hinged so that they only open in one direction. So if we're pushing air up, it's only going to travel through the left-hand side, and then it's going to travel through here, and then it's going to travel through there. And so it's going to drive the turbine. That's when the water's pushing up. Then, when the water's pushing down, it's going to create a vacuum, and air is going to get sucked into that vacuum. And if you look at the valves, we can see that if air is coming in, it's going to pass through this one, pass through the turbine, and then down here into the column. And so this system of gates allows for air to always be passing through the air turbine in the exact same direction, so the turbine's always turning in the same direction. But again, it's an interesting approach, and it relies again on the rise and fall of the ocean and on waves. And so if there aren't large waves at a particular time, you're not going to get much electricity. When there are larger waves, you're going to get a lot more electricity. And then this is just an example of one that's built onto a cliff or onto the side of a cliff face. And it's the same idea, it's just a little bit different shape. The water level rises, it drives air through the column. As the level lowers, it sucks air back through. There's a system in there designed to keep the fan spinning in the same direction. Now, of course, with our waves, the amount of electricity that can be generated is going to be determined by the size of the waves. And the wave size is then determined by a couple factors: the wind speed, the distance over which that wind is applied, and then the depth and what's on the floor of the ocean are also going to significantly impact the size and shape of our waves. And the potential energy then of a set of waves is directly proportional to two things: the square of the wave amplitude, and we saw this back when we talked about waves, and its velocity. And the velocity simply because the faster the waves are moving, the more wave crests you're going to get, so the more energy there is in a given time. The total energy of these waves is then the sum of the potential and the kinetic. And even though it's not directly accurate, we can assume a sinusoidal wave for our water waves. And defining a couple of variables, again, our rho is density, in this case it's water density. Our g is the acceleration due to gravity, a is the amplitude of the wave, and lambda is the wavelength. The potential energy in the wave is 1/4 times the density times g times the area squared times lambda. This is also our equation for the kinetic energy, and this goes back to our equations for energy in a wave. Since the total energy is the two of them added together, we see the expression down here where energy is 1/2 rho g a squared lambda. And so our power then is all of that over time, energy per unit time, which, if we do lambda over t, that's our frequency. So we can simplify all this into an equation for power that's 1/2 rho g a squared times the frequency of the wave. That's this right here. Now, in the IB data booklet, you're going to see it, I think, a little bit differently. And they say it's, or give it in terms of power per meter. And so power per meter of wave. And that's just going to look like this, where 1/2 a squared rho g, and v again is the speed of the wave. So essentially the same equation, slightly different format.